discuss about a very frequent inequality that appears in analysis. Associating L1 and L2 norms of a function. So with this inequality, we associate L1 and L2 norms in a 1D bounded interval. And this is the statement here. If the function f is in L2 norm, belongs to the space of square integrable functions in this bounded interval, then the L1 norm of the function is bounded by this quantity, square root of b minus a, with the square root of the length of this interval, times the function equipped with L2 norm. Let's give start by writing down the left-hand side of the inequality. So the L1 norm is the space of absolute integrable functions, and we take the norm of the function here. Now this can be written as integral from a to b, 1 times f of x dx, and from here I can write down the Cauchy-Schwarz inequality. Cauchy-Schwarz. And this can be written as 1 squared dx and square root times the other integral from a to b, f of x squared dx square root. Here I can just compute this integral explicitly is b minus a square root times the integral from a to b, f of x squared dx square root of this integral. This is just the L2 norm of the function f on the interval ab. So what I have here is that f in L1 is bounded by the square root of the size of the interval times the function f in L2 norm of AB. This is the L1 norm of the function f, bounded by the square root of b minus a. b minus a is the size of my 1D interval, square root times f equipped with the L2 norm on this interval. To summarize, we just take, in order to prove the inequality, the L1 norm of the function. Then we do some manipulations here. We impose the Cauchy-Schwarz inequality for integrals. From here, this integral can be computed explicitly, and we have this quantity multiplied with the L2 norm of the function. It's a very frequent inequality in analysis. And it helps to associate the function. So here you see interesting things, the L1 norm, the L2 norm, and here is the size of the interval where this function is well defined.